Hello, this is Tim Smith, the Academic Support Coordinator for St. John's River State College, St. Augustine campus. This video is part 2 on applications of integration and is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. It is recommended to view applications of integration part 1 prior to watching this video. In this video, we will be discussing solids of revolution using the disk method and washer method, and volume by shells. To solve the volume problem for many solids only requires geometry. Depicted is a sphere, rectangular prism, cone, and cylinder, with the volume formulas listed below. Many shapes, however, do not fit into these cases, some having curved sides instead of straight. Let's take our cylinder from a moment ago and lay it on its side so that the x-axis of our coordinate plane passes through the center of the cylinder, and isolate a two-dimensional portion that lies above the x-axis. The area of our cross-section would be A is equal to R times H. We can now recreate our cylinder by taking the top of the shape and rotating it into 3 dimensions in a circle centered on the x-axis and generate a solid of revolution. If we use the same logic, but apply it to an irregular shape, we can find the volume, just as we found the area under curved functions. For this, we consider that a solid of revolution is rotated around the x-axis, but sweeps out a cross-sectional disk with a radius equal to f of x. The area of this disk will then be a of x is equal to pi times the radius squared, which equals pi times f of x squared. This manner of calculating the volume is called the disk method. V equals the integral from a to b of a of x dx, or the integral from a to b of pi f of x squared dx. As an example, let's find the volume of solid described by f of x is equal to e to the negative x, and rotate it around the x-axis on the interval from 0 to natural log of 4. This would be the integral from 0 to natural log of 4 of pi times e to the negative x squared dx. We can start by moving the constant pi outside of the integral. We then take the antiderivative, which would be negative 1/2 e to the negative 2x, evaluated from 0 to natural log of 4. The result is pi times the quantity of negative 1 over 32 plus 1/2, which simplifies to 15 pi over 32, or approximately 1.473 cubic units of volume. More exotic solids of revolution may be computed using the same idea employed for finding regions between curves in two-dimensional problems. Let f and g be continuous functions with f of x greater than or equal to g of x greater than or equal to 0 on a, b. Let R be the region bounded by y equals f of x, y equals g of x, and the lines x equals a and x equals b. When R is revolved around the x-axis, the volume of the resulting solid of revolution is volume equals the integral from a to b of pi times the quantity of f of x squared minus g of x squared dx. For example, compute the volume of solid revolution generated when the region R bounded by f of x is equal to 2 times the square root of x and g of x equals x is revolved around the x-axis. Remembering that the volume equals the integral from a to b of pi times the quantity of f of x squared minus g of x squared dx. First, let's look at the two functions to determine the boundaries. If we set x equal to 2 times the square root of x, we arrive at two solutions 0 and 4. These solutions will determine the upper and lower boundaries of the integral. The graph depicts this as the 2 points 0, 0 and 4, 4, where the graphs intersect. With respect to x, the function 2 square root of x is the greater function, so we will integrate 2 times the square root of x squared minus x squared dx. The next graph depicts the rotated integral with the rounded washer shape with an outer circumference governed by 2 square root of x and the inner circumference governed by x. This represents one slice of the solid of revolution. Looking at the integral, we can pull pi to the outside and separate what is left into two integrals. Next, we take the integrals, which gives us pi times a quantity of 2x squared evaluated from 0 to 4, minus x cubed over 3 evaluated from 0 to 4. This results in pi times a quantity of 2 times 4 squared minus 2 times 0 squared minus the quantity of 4 cubed over 3 minus 0 cubed over 3. When we simplify, we get pi times a quantity of 32 minus 64 over 3, or 32 pi over 3, which would equal approximately 33.51 cubic units of volume. Just as in the two-dimensional case, the volumes of the revolution may also be integrated with respect to the y-axis. Let f and g be continuous functions, with f of y greater than or equal to g of y greater than or equal to 0 on CD. Let R be the region bounded by x equals f of y and x equals g of y, and the lines y equals c and y equals d. When R is revolved around the y-axis, the volume of the resulting solid of revolution is given by, using the disk method, volume equals the integral from c to d of pi f of y squared dy. Using the washer method, volume equals the integral from c to d of pi times the quantity of f of y squared minus g of y squared dy. As an example, compute the volume of the solid revolution generated when the region R, bounded by f of y equals y, and g of y equals y over 2, and y equals 6, is revolved around the y-axis. We start with the equation for the washer method and apply the functions so that the volume equals the integral from 0 to 6 of pi times the quantity of the function that determines the outer horizontal radius minus the inner horizontal radius. In this case, y squared minus y over 2 squared dy. When we move the constant pi outside and split the integral at the minus sign, we get pi times the quantity of the integral from 0 to 6 of y squared dy minus the integral from 0 to 6 of y squared over 4 dy. When we take the integral, we get pi times the quantity of y to the third over 3 evaluated from 0 to 6 minus y cubed over 12 evaluated from 0 to 6. From here we get pi times the quantity of 6 to the third over 3 minus 0 to the third over 3 minus the quantity of 6 to the third over 12 minus 0 to the third over 12. We simplify to get pi times the quantity of 216 over 3 minus 216 over 12, or pi times the quantity of 72 minus 18, which equals 54 pi, or 169.65 cubic units of volume. The volume by shells method involves cutting a three-dimensional object into slices that rotate around the x or y axis in the shape of cylinders which can be added to each other. The volume of each cylinder can be easily determined if you unwrap the cylinder. Volume equals 2 pi r times the height h times the thickness, or in the context of a shell placed on a coordinate plane graph, volume equals 2 pi x of k times f of c times delta x. Let f be a continuous function on the interval ab. If R is the region bounded by the curves y equals f of x and the x-axis between the lines x equals a and x equals b, the volume of the solid generated when R is revolved around the y-axis is volume equals the integral from a to b of 2 pi times x times f of x dx. In a similar fashion as before, if the shape is bounded between two continuous functions f and g, where f of x is greater than or equal to g of x on AB, and if R is the region bounded by the curves y equals f of x and y equals g of x between x equals a and x equals b, then the volume of the solid generated when r is revolved around the y-axis is volume equals the integral from a to b of 2 pi x times the quantity of f of x minus g of x dx. As an example, use the shell method to find the volume of the solid of revolution generated by f of x is equal to x and g of x is equal to x squared about the y-axis. To determine the boundaries of our integral, we set x equal to x squared and solve. X squared minus x equals 0. X times the quantity of x minus 1 equals 0. X equals 0. X equals 1. This is also depicted on the graph as the 2 points where the functions intersect. Therefore, the volume of the shape formed by revolving the area between the functions around the y-axis equals the integral from 0 to 1 of 2 pi x times the quantity of x minus x squared dx. In this equation, x represents the radius of the shell, and x minus x squared the height of the shell. Like before, we can take the constants out of the integral, in this case 2 pi, then distribute the x into the parentheses. When we take the integral, we get 2 pi times the quantity of x cubed over 3 minus x to the 4th over 4 evaluated from 0 to 1. This gives us 2 pi times the quantity of 1 over 3 minus 1 over 4 minus the quantity of 0 over 3 minus 0 over 4, which simplifies to 2 pi times 1 over 12, or pi over 6, or approximately 0.524 cubic units of volume. Let us take the same example, except this time we'll wrap it around the x-axis. Instead of y equals x and y equals x squared, we'll use x equals y and x equals the square root of y. The boundaries will be 0 to 1 again, based on the intersection of the two functions. From the perspective of the y-axis, the square root of y is the larger function. Therefore, the volume equals the integral from 0 to 1 of 2 pi y times the quantity of the square root of y minus y dy. In this integral, y represents the radius of the shell, and the square root of y minus y is the height of the shell. The 2 pi can be moved again outside the integral, then simplify to be from 0 to 1 of y to the 3 over 2 minus y squared dy. We take the integral, giving us 2 pi times the quantity of 2 times y to the 5 over 2 over 5 minus y to the 3rd over 3, evaluated from 0 to 1. Then we get 2 pi times the quantity of 2 times 1 to the 5 over 2 over 5 minus 1 to the 3rd over 3 minus the quantity of 2 times 0 to the 5 over 2 over 5 minus 0 to the 3rd over 3. When we simplify, we get 2 pi times the quantity of 2 over 5 minus 1 over 3, or 2 pi times 1 over 15, or 2 pi over 15, or approximately 0.419 cubic units of volume. Note that we arrived at a different answer than when we rotated this around the y-axis. This is consistent because rotating into the 3 dimensions gives us a completely different shape depending on the axis of rotation. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you and good luck with your studies.